Yeah, over to Dr. Swati.
Well, it's a pleasure to introduce the speaker for the next session, Professor Ida Todre Sanyal. To introduce her, she received her BS degree in Electrical Engineering from Brandley University in 2001 and MS degree from Long Beach State University in 2003. She did her PhD in Electrical and Computer Engineering from University of California at Santa Barbara in 2009. She is currently serving as a Director of Research for the French National Council of Scientific Research, which is attached to the Montpellier Laboratory of Computer Science, Robotics, and Microelectronics. Dr. Todre Sanyal was a visiting fellow at Cambridge Graphene Center and Wolfson College at University of Cambridge during 2016 to 2017. Previously, she was a R&D engineer for Fermi National Accelerator Laboratory. She also held visiting research position at Mentor Graphics, Canadians Design Systems, STM Microelectronics, and IBM TG Watson Research Group. Her research areas includes emerging technologies and novel computing paradigms such as neuromorphic and quantum computing. With these few words of introduction, I welcome you, Professor Ida, and the session is over to you. Thank you.
Thank you. Thank you for the kind introduction. Let me share my screen. So thank you, good morning or good afternoon, everyone. Thank you for the kind introduction. Thank you for also having me. Sorry, this is the wrong. Let me stop sharing for a moment. This is the wrong. Sorry, too many presentations. Here I am. I apologize for that. Here I am. So good afternoon or good morning, depending on where you are. So I'm excited to be here, give a presentation for the World Nano Congress on Advanced Science and Technology, especially today on the 8th of March, and celebrating the Women's Days, especially Women in Science. And I would like to talk today a little bit about our ongoing project on neuromorphic computing and look into it from the devices, materials, devices, all the way to architecture. So this work in neuromorphic computing with oscillatory neural networks is in the context of a Neuron project. So this is a European project, and this was started in 2020 with a focus on unconventional metal electronics. So the idea here is to look into beyond CMOS devices for energy efficiency and also into novel architectures such as brain-inspired architectures. And also to look into the novel design methods in terms of how can we build such system, and especially if we want to upscale the system, so a large-scale neuromorphic system. So with this a little bit of an introduction, I would like to sort of state the art, so to kind of set the stage into why we need to look into novel computing paradigm, and especially neuromorphic. That is in the current state of the art. So if you look into the challenges that we are facing in the von Neumann type of architecture, the main challenges are the scaling, and especially device scaling. And we are in sub-nanometer regime, and we are witnessing that the devices also have a problem with gate leakage. So the Moore's law, so continuing the Moore's law, it's becoming more and more challenging, especially in beyond 2 nanometer nodes. The other challenge is the memory wall. So what we see is the data transfer. There is a lot of cost in terms of transferring data from memory to processor, especially in the context of big data and also cyber-physical system where there is a lot of data to be processed. And the next challenge is also the heat wall. Because of the very large density of integration of devices and also very large circuit and switching activity of devices, we are seeing that there is a lot of thermal buildup, and that causes a lot of the challenge in terms of how to dissipate this heat. So the challenge has been overcome by limiting the performance of the systems on chip. So, and if you look into this, also this graph here, it's very interesting to see that the current computing systems and also supercomputing chips are in megawatts type of power consumption. And this is a quite challenge, especially if we want to build more and more cyber-physical system and also supercomputers to be able to handle the large data processing. So one viable solution which the community has been looking into is the brain-inspired computing or neuromorphic computing. And the main interest of that is to have analog and mixed signal design, and also to emulate the brain's rhythmic activity in order to be able to have as closer to the biological neural networks, because this will allow a fully parallel computation and also an energy efficient computing. So the focus has been for us to look at this challenge from, as I mentioned, from materials, devices, architecture, all the way to implementation. And there have been some implementation. So if we look into, so it's important to know that the brain, which has billions of neurons, so 85 billions of neurons and quadrillions of synapses, consumes about 20 watts. And there have been some recent developments, such as Spinnaker, which is a European large-scale neuromorphic system, which has millions of synapses with thousands of neurons, and it can consume about 1 watt. There's also BrainScale, another large-scale European level consortium that have built a very energy efficient system consuming about 1 watt, which has about 512 neurons and 128,000 of synapses. And more recently, we have seen some developments from Intel, Loihi, and IBM's True North, which are in milliwatts of power consumption, but still these are limited in terms of, even though they have millions of neurons and synapses, we are still far away from having a fully analog type of computing system with much more energy efficient or closer to the energy efficiency limits. So that means we need to continue on this path into more neuromorphic analog-based computing for neuromorphic design. So that brings us also in the context why there is, as I mentioned, why there is a need for all of this energy efficient computation is because we are at the Industry 4.0. So what is Industry 4.0 is the distributed or all of this cyber physical system that are becoming part of every industry now. So from healthcare to defense, manufacturing, government, automotive, transport, you name it. There is a very fast adoption of AI and these cyber physical systems in every domain, and also in aspects of our daily life, from the way we work, entertain, educate, and so forth. So what we are witnessing with all of these cyber physical systems is that as we are making edge devices, so autonomous vehicles, smart agents for transport, or smart city or smart homes, we are seeing that they are limited, such systems are limited into memory and processing. So we are limited in terms of how much data or how much training can be done on these smart devices so they can be trained from the data input, because the data at some point is difficult to transport to transfer to the cloud, because sometimes you have a limited bandwidth. So for example, in a city camera, you have thousands of these images, and by the time that you are transporting them to the cloud, that you are transferring them, you are losing you are limited on bandwidth. Also, maybe you also have security issues, because for example, in healthcare, you probably cannot transport a lot of this healthcare data of patients. So there are some security concerns as well. So you want to be able at the edge to process the data. So there is some learning capability, training capability, and inference. So for that reason, we need to be able to come up with new architectures and also ask the question, what are the devices to enable such capability? So online training and also online inference. Why does this matter? This matters because, as I mentioned, there is a limited in bandwidth, so you cannot afford to send a lot of the data into the cloud. You also have a latency. That means you need to be able to process a certain amount of images per second, and also this privacy concern. You cannot always send the data over the cloud. But the major issue with all of these systems is the power. So the power consumption and their energy efficiency. And is given overall that they need to be autonomous to be able to process, to train, and also to infer from the data. Energy efficiency, how fast and also how they perform is very much a factor by the power consumption of this system. So there we see an opportunity to be able to not only provide this online training and inference at the edge, but also to architect the system. So what has been our focus is to look into how to better emulate neurons and synapses. So biological neural networks have rhythmic behavior, so they spike and fire. And they are ubiquitous in the neurocortex, hippocampus, and olfactory bulb. So, and from neuroscience, we know that synchronization, so the brain waves also guide the memory, or how the memories is also being stored, and also how that is also triggered and enabled. And the idea here is to look into the biological neural networks and emulate this activity of the spikes in waves, or you can, as you can see here, as oscillatory type of waveforms, where we look into the relation or correlation between this oscillatory waves or signals. The idea here is to be able to compute in phase. So by looking into the such, for example, oscillatory behavior, we can compute in phase. So rather than compute in the time domain, we are looking at the correlation of the signals and be able to encode a 0 or a 1. So in a logical or in digital circuits, we have, if it's at a high voltage, for example, in VDD, that would be corresponding to a 1 logical bit. And if it's at a ground level, that means it would be like a 0 logical bit. In computing in phase, so emulating the artificial neurons and synapses, the idea here is to look at the correlation between the signals. So for example, if two signals are at 180-degree phase difference, that means one signal is a logical 0 and the other one is a logical 1. So it's the phase difference between these signals that we can encode the data. So this is a unique opportunity to be ultra low power type of processing. So how can we build such systems? So here is the architecture type of what we can perform by computing in phase. So how to emulate this computing in phase. So for that, we would need neurons that are oscillators in behavior. And we also need the memory, so the synaptic array. And the synaptic array is based on 2D molybdenum disulfide type of memristors. So these are the memristors which their resistance will change as a function of current flowing through them. And the oscillators, so the neurons, which are based on phase change materials. So this is a metal insulating transition material based on vanadium dioxide. So this is the system that the architecture we would like to build in order to have this computing in phase, which is much more energy efficient than the current paradigm. So just to kind of give you an idea, in the current paradigm, if you have an input like this, so a temporal signal like this, you need to integrate it in order to be able to have, to understand if this is a logical 1 or a 0, and similar here. And in computing in phase, as I mentioned, we simply need to look at the correlation between signals. So we need to have this phase to digital converter to be able to understand if the signals are in phase or out of phase, to be able to encode a 1 or a 0. So to kind of give you a little bit more intuition, how is it to compute with oscillators, and especially to compute in phase? You can think of this as the metronome. So you might have seen this type of experiment where you have several metronomes that you can start them at any random time. And after certain cycles, you'll see that they're all switched, they'll all be synchronized, because the base is also moving a little. And in our sense, the base here is represented by these synaptic memristive devices, which they change the resistance, so the weights of the synapse. And these are the oscillators, which will, after some cycles, they will be synchronized. So to keep this in a more practical visualization, you can think of here as an image. You can think that each of these pixels is an oscillator, and some pixels are white, some of them are black or gray. So this is a fuzzy or a corrupted image. And based on how the system is being connected, so you can have coupled oscillators, so fully coupled oscillator, which is very much like a whole field neural network. And based on the coupling, so on the weights that are being distributed, you can have the correct output, which will be encoded on the phase difference between oscillators. So this creates an associative memory. So this is the notion or the concept of how we compute with oscillators. Further, we want to also explore, so we are also developing, so I'll talk a little bit about the Vo2 devices and also the memoristic devices, so based on 2D materials. The idea is to be able to use such architecture, for example, to see what would be its added value if you were to explore it in convolutional neural network type of architectures. Will it be, because this can provide this low power filtering type of application. So let me talk a little bit because on the devices, because this is the key of how we can emulate these biological neurons, but also where does this low power or energy efficiency come from? It's important to mention that a Vo2 is a phase change material, so it has this monoclinic M1 insulator, so at temperatures, and then it can further change to rutile, so metallic. So there is this hysteresis, and this is for the cooling and the heating and the cooling. So you can see the hysteresis formed from the heating and the cooling. And this is with respect to TH, so this is where the threshold temperature in which the material changes and material resistivity changes by several orders of magnitude. And this hysteresis also would tell us how fast the Vo2 device can switch. So this hysteresis window is very important. The next one is also, there are moments where both this metallic and insulating, the metallic phase coexist. And over finite temperature, so you can see here, you can start with an insulating, and by the time it becomes metallic, so you can see that there are some metallic phase coexistence with insulating. And the key knob for us to understand this, the physics of this resistive switching of Vo2, has to look into the electron density, which is almost the one or the main knob that accounts for this change in resistivity and conductivity. The other, what we also been trying to understand a little bit is how to emulate this by understanding the grains and also the interference between the grains. So this grain to grain boundaries, but also how does the device self-heats, because self-heating plays an important role to inducing the IMIT, so the insulating to metal transition. So we have performed various electrothermal simulations of Vo2 devices, and enables us also to build a compact model, so a TCAD model, but also a compact model, in order to be able to get these IV characteristics. So here you can see it's the initial, when there is, so the voltage is ramping up, we can also see this linear behavior. And then immediately we have this negative resistance range, and then this very high, so the higher resistive state and the low resistive state, and this is where the oscillations are occurring. So we are trying to build based on the load. So how we load the Vo2, we can see the oscillation, so we can obtain in this NDR region. So this is a very interesting to be able to control. So this is how we can build then circuits and architectures by electrically controlling the current flow on the Vo2 device. So here is to kind of give you an idea. So we have the Planar Vo2 device, which has been developed in the project, and we have a compact model to be able to represent the switching, so the phase and also the resistance switching on this device. And we also have the mathematical models in order to be able to represent the dynamics, the nonlinear dynamics of the Vo2 device. So this is for a single oscillator case, which allows us to now to further understand, so as I mentioned on this negative differential resistance region, so how we load the Vo2 device, it actually matters and also controls the oscillator output frequency and also the amplitudes and also the period, the signal amplitude, which are important features for how you can build a circuit in an architecture. So we have developed also all the mathematical, so understanding the dynamics of this oscillator device. And now into practical, so how can we build a system that computes with oscillators? So you can start here with two oscillator case. So they are coupled. So the coupling here, it's the RC coupling. And depending on the values of this RC, so the resistive coupling or the weights, as you can think of it on synaptic, and you'll see that they are in phase. So the both signals have no phase difference. That means they both have logical zero. So they are both like white pixels. If we change the coupling resistance, so if we have the coupling resistance of 100K, so the much more weaker coupling between oscillators, that would make these oscillators to have a phase difference of 180 degrees. And they would make out of phase or a logical one. So you can think as a white and a black. So this is the notion of how we can take this Vo2 devices, which we are developing in the clean room in the project, and to take this compact models that we are also developing in order to be able to perform circuit and then architecture level implementation. So as I mentioned, the architecture and design space exploration is very important because that allows us to also find a suitable architecture and control strategies for this oscillatory neural network. I also want to mention that this is very much in the spirit of Hopfield neural networks. So you might have seen this type of architecture from Hopfield neural networks, where the main function is associative memory. And the main goal here is how to adjust the weights. So what would be the adjustment of the weights, how to control in order to be able to perform a meaningful application. So there is the initialization, which matters, the control signals, and also how do you get the phase differences out of the system. So in order to be able to understand the white or black or something in between pixels. I'm also happy to say that this concept of computing in phase based on Vo2 devices and MOS2 devices, we are implementing this in analog. So we are trying to develop, currently the efforts are on developing a demonstrator based on these devices. However, as a proof of concept, we also have implemented this ONN, so oscillatory neural network computing in phase digitally. So that means we have implemented this function with arithmetic logic for neurons and for synaptic, and we can have this phase calculation also arithmetically done, and also implemented this on an FPGA. This was an important first step for us to understand, can we compute with oscillators? And also, what are the resources needed? Also, what is the latency, the bandwidth? And we perform online training and also learning. And we have performed this on two types of applications. So with 60 neurons, which is implemented on an FPGA, and where we have the data streaming from a camera. I'll show you some videos on this. And it provides a fuzzy image. And then we can see on the screen the output of the correct image that is stored on the neural network. The other one is on the obstacle avoidance. So we have 60 neurons again implemented, and we have barcoded the various obstacles. So for example, this is a thermometer encoding of proximity sensors. So it means if it's if there is a blockage, so if there is a blocks and how close that is to represent it in a bar type of thing method here. And then the output would be giving a command. So for example, the verse 2, that means the right side or the left side is blocked. So it means you can take the other direction. So you can issue commands to the robot. So maybe I can start with the FPGA demonstrators on this type of concept while we are working on the full 2D version of this ONN. So as I mentioned, we have here so you'll see the video shortly. We have here the camera, which is streaming images. So it's providing the fuzzy digits. So this is for digit recognition type of application. We have implemented this on FPGA on a Zibo ZSet digital development board, and you will see that the images will be printed on screen. And the type of features that we are getting, so we are still looking into how long does the ONN compute, so we can see in average this can be computed in a very short amount of cycles. and also what is the accuracy. There is also, I forgot to mention that we are applying the Hebbian learning rule in order to train the ONN. So the accuracy also needs to be further improved, more refined, so we can have higher accuracies on the image training. And the second one, this is on the obstacle. So as I mentioned, we are encoding the bar blocks. So in terms of how close it's a blockage and its proximity, and we are training the ONN with this type of patterns, and also issuing a command to the robot to go left or to go right with respect to the blockage he senses from the sensors. And we can see here that this can be performed in reasonable frequency ranges and accuracy depending on the discretization of the images. We can have is between 75 to 100% accuracy. And this is also implemented, so all of these are put together on an Arduino board with a sensor and ONN. So here, for example, I'll show you, as I mentioned, here is the camera. I do not know if you can see it. So there are images which are being streamed from a phone, so the fuzzy, and then the camera, and then here is the ONN, and the output will be also shared on the screen here. So the corrected, so maybe I can start so you can see this. So this allows, as I don't know if you were able to capture, but so this is, for example, a fuzzy 4. You can see that there are some additional noises on some of the pixels, and we can see here the final output that we are able to obtain from the ONN. So the fully recovered, or what was memorized on the ONN. And here is the other application. So here we have the robot. It has 3 sensors around it. It has also this Arduino. And the idea here is depending on the images, so on the blockage, so avoidance of the blockages, the robot can find a path. So that means he's avoiding, and then he can issue a command to the robot to eliminate these obstacles. So you can see here, so yeah, this is just a little, as I mentioned, a little demonstrator of the concept. So that means we can compute with oscillators. It depends on the architecture, how we're going to emulate this. So this was the digital emulation of this concept. And now we are working on the analog implementation, and especially using Vo2 devices as oscillators and 2D memristors based on MOS2. So with that, I would like to probably wrap up, and I hope this kind of gave you an idea to what is to compute, and also how can we go toward energy efficient computing. And this is in the framework of Neurons. So we are several partners, so CNRS, myself and my group, IBM Research in Zurich, which they're working on the development of the Vo2 devices, so these oscillating devices. Fraunhofer on the development of 2D MOS2 devices for memoristic applications. CSIC on the architectural level exploration of the neuromorphic system. And Silvaco on building all of these TCAD tools and also the models in order to understand the phase switching behavior on Vo2, but also on memoristic devices, and AI Mergent, which is exploiting this technology for their robotic application, AI and robotic. So in a nutshell, I hope this kind of gave you an alternative to how we can go from materials, devices to architecture and application for energy efficient neuromorphic computing. So with that, I'd like to thank you for your attention, and I would like to, if there are any questions, I'll be happy to answer them.
Thank you, ma'am, for such an interesting presentation. We have some questions from the participants. The first question is from Professor Gargi Rena. How do you implement 60 neuron on the FPGA?
Yes, so that's a very good question. So in FPGA, the idea is to implement digitally the function of the neuron. So how does this neuron compute in phase, and also the synaptic implementation of by arithmetic logical units. So we have, get in touch with us, but the idea here is to implement digitally these analog functions. So there have been a lot of state of the art. So if I can also provide it, but get in touch with us. So this is some implementation that we have achieved during this project. We have also published in terms to implement these analog functions, but in a discrete way. So it doesn't have the same refinedness of an analog, of course, but it has the functionality. So the functions are being captured in order to understand, does this concept work or not? So this was our first achievement in the project. We are very happy and proud to have achieved such implementation of the digital ONN. And if somebody wants to know more, I'll be happy to share some of our publications on this topic and also refer to you to some other reading literature. So get in touch if that's of interest.
Thank you. There's one more question from Vishakha, that is it possible to use any diode having NDR region as an oscillator?
So rather than an oscillator, but using a diode. So I'm not sure if you can obtain the same functionality because what's interesting of the oscillator or of the Vo2 device, it has this it has two phases, right? So you can switch from one or the other. So it's a self-heating that helps, but also you can have the current controlled phase switch. So I'm not sure that maybe in a more, so there is some analog implementation of oscillators, so based on op-amp design or maybe other types. So there are some in the literature, but the I'm not sure that a single diode would, or any diode would be able to capture that region. It's a little bit more complex than that. But again, if the person is interested, I can also refer to what we have achieved to analog implementation of oscillator. That's a very good question, because that is the key of how we can perform low power computation. Because if you don't have, I mean, you can perform this function, but if it's very power hungry, then the whole interest, it's sort of dying down, because the whole point is to compute in phase, but at a very low power mode.
Thank you. Thank you for answering all the questions. And once again, I would like to thank for accepting your invitation. And
yeah, thank you. Thank you, Aida, once again for such a nice, wonderful talk. Thank you. Thank you very much. Have a nice day.
Thank you. Have a great day.
Thank you. Thank you. See you.
Bye-bye.
Bye. So we are signing off for the day. May I request the participants to join the inaugural ceremony at exactly sharp at 2:30 p.m. Thank you.